Hi students, in today's class we will study the analysis of line-to-line fault on an unloaded alternator. The power system faults can be classified into symmetrical faults and asymmetrical faults. Three-phase to ground fault is a symmetrical fault. In the asymmetrical faults we will study the single line to ground fault, line-to-line fault and a double line to ground fault. In today's class we will see the analysis of line-to-line fault. For the analysis of line-to-line fault, we will use the symmetrical component transformation, or we will be using the sequence networks. Let me draw the equivalent circuit of an alternator. In the equivalent circuit, we have a voltage source in series with an impedance. This is our A phase. This is the B phase. This is our C phase. This is the neutral grounding impedance. Let it be ZL. The voltages in the three phases are EA, this is EB, and this is EC. The phase impedances are ZA, ZB and ZC. The three phase impedances are equal, so we can mark this as Z. This is an unloaded alternator, so the currents in the three phases are 0. IA, IB, IC. All the three currents are equal to 0. Now this is a balanced system, because if you look at the currents, all the three currents are equal. If you look at the voltages are also equal in magnitude, but they are separated by 120 degrees. So this is a balanced power system. So you will get only positive sequence network for this particular power system. There is no negative sequence network, there is no zero sequence network for a balanced system. Now suppose a fault occurs in this particular power system. There is a line-to-line fault. The second line is shorter to the third line. Now these two currents are no more equal to 0. Now this power system has become unbalanced because the three currents are not equal to 0. In the first phase the current is 0, whereas in these two phases, a heavy fault current exists. So for this particular power system, now if you look at the sequence networks, along with the existing positive sequence network, you may get negative sequence and zero sequence network. But the thing is, you need to find out the interconnection of the three networks, whether the three sequence networks are connected in series or in parallel. For that, we need to find out the sequence currents and the sequence voltages. Let us find out the sequence currents first. The sequence currents IA0, IA1 and IA2. This is equal to 1 by 3 into the transformation matrix. It is 1, 1, 1, 1 alpha, alpha square, 1 alpha square, alpha. Into the phase voltages, sorry, the phase currents, IA, IB, IC. IA equals 0. In the first phase, the current equals 0. When you look at this IB and IC, they are equal in magnitude but are opposite to each other. So we can write IC equals minus IB. So IB is kept as such. IC equals minus IB. Now let us find out the sequence currents. IA0 equals 1 by 3 into 1 into 0 plus IB minus IB. So 0 plus IB minus IB. This is equal to 0. So there is no zero sequence current for this particular type of fault. Or we can say the zero sequence network doesn't exist for this particular type of fault. IA1 equals 1 by 3 into 1 into 0 plus alpha IB minus alpha square IB. And IA2 equals 1 by 3 into 1 into 0 plus alpha square IB minus alpha IB. Here in IA1, it is alpha IB minus alpha square IB, whereas in IA2, it is alpha square IB minus alpha IB. So we can write IA2 equals minus IA1. These two currents are opposite each other. Let me write the sequence currents here. IA0 equals 0. IA2 equals minus IA1. These are the sequence currents for this line to line fault. So there is no zero sequence network. The negative sequence current is equal to minus positive sequence current. Now we consider the voltage at these 2 points. The voltage or the potential at this point is VB. The potential at this point is VC. As these 2 points are shorted, we can write VB equals VC. Now let us find out VB and VC in terms of sequence voltages. VA, VB, VC. This is the equation we are using to convert the sequence components into phase voltages. There the transformation matrix is 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square into the sequence voltages VA0, VA1, VA2. Here VB equals VC. VB equals VC. VB equals 1 into VA0 plus alpha square VA1 plus alpha VA2. VC equals VA0 plus alpha VA1 plus alpha square VA2. Here VA0 will be getting cancelled, and this is alpha square VA1, this is alpha VA1. So alpha square minus alpha into VA1. This is alpha square VA2. This is alpha VA2. So this is equal to alpha square minus alpha into VA2. So this alpha square minus alpha will be getting cancelled. So we can write VA1 equals VA2. The positive sequence voltage equals negative sequence voltage. So let me write the sequence voltage here. VA1 equals VA2. So this is the condition for the sequence voltage. So from these two expressions we can understand there is no zero sequence network, and positive sequence network and the negative sequence network are connected in parallel. These two voltages are equal, currents are opposite to each other. Let me draw the positive sequence network here. When you draw the positive sequence network for an alternator, we have a voltage source in series with positive sequence impedance. This is the positive sequence impedance. This is the voltage source. Positive sequence current is IA1. This positive sequence voltage VA1 equals EA minus the drop in this impedance. EA minus the drop is IA1 Z1. Let us draw the negative sequence network here. When you draw the negative sequence network of an alternator, there is no voltage source. We have only negative sequence impedance in this network. Negative sequence impedance is marked as Z2. The current is IA2. The negative sequence voltage is VA2 equals the drop in this impedance minus IA2 Z2. These two networks are connected in parallel. So this is the sequence network diagram for the line to line fault without any fault impedance. This is a dead short from the B phase to C phase. Now you can easily find out the sequence currents in this network. IA1 equals the total voltage divided by total impedance. EA divided by Z1 plus Z2. Now let us add one more step to this particular fault. Suppose the fault occurs through a fault impedance ZF. Now this VB and VC are not equal. VB equals VC plus the drop across this impedance. So VB equals VC plus the drop is IB into ZF plus IB into ZF. We can find out IB from a similar expression. IB equals 1 into IA0 plus alpha square into IA1 plus alpha into IA2 into ZF. As you know, IA2 equals minus IA1. So this can be written as minus alpha IA1. And here IA0 equals 0. There is no zero sequence current here in the line to line fault. The zero sequence current is 0 for this particular case because the zero sequence current flows through the ground connection. In this particular fault, there is no ground connection. If there is a ground connection, this currents can flow through this neutral grounding. There is no ground connection at this fault point, so we do not have any ground current, so we do not have any zero sequence current. The zero sequence current flows through the neutral grounding. In this particular case, there is no neutral current So there is no zero sequence current. So these two terms are equal, plus alpha square minus alpha into IA1 into ZF. Here alpha square minus alpha terms will be getting cancelled. So VA1 equals VA2 plus IA1 into ZF. So positive sequence voltage equals negative sequence voltage plus a drop. Here this is the impedance ZF. Here the current is IA1. This is the current IA1. So VA1 equals VA2 plus the drop across this impedance. So this is the complete sequence network for the line to line fault, including the fault impedance. Now we have drawn the sequence network. From the sequence network we can easily find out the fault current. Let us first find out the sequence currents. What is IA1? The current flowing through this sequence network equals total voltage divided by total impedance. The total voltage is EA divided by the total impedance is Z1 plus Z2 plus ZF. And IA2 equals minus IA1. For the line to line fault, there is no zero sequence current. Once you get the sequence currents, then you can easily find out the phase current from a similar expression. Our objective is to find out the phase currents, because the common man doesn't understand anything about the sequence current. So finally we need to find out the phase currents. We need to find out IA, IB and IC. Similarly, you can find out the sequence voltages VA1 and VA2. Obviously, VA0 will be equal to 0 because the zero sequence current is 0. Once you get the sequence voltages, you can easily find out the phase voltages using this expression.